Good afternoon, YouTubers. Today we're going to be working on a little bit on a falling object under air resistance as shown here. Basically, we have a baseball that is on the force of its own weight. So it's being accelerated time m times g, gravitational acceleration. And but there's two forces that are opposed to that, which are the buoyancy force and the drag force. Now, we're gonna let this ball drop from certain elevation, and it will acquire faster. It will go faster as the time goes by. So our vector here clearly says that it's positive downward direction, and basically we apply the Newton's law that the net force acting on the baseball equal mass times acceleration. That net force equal, now what is acceleration is the change of velocity versus time, and then we take dv over dt equal, then divide this f net times the mass, so we end up in this differential equation. Now we just need to find out what is f net, which is, that's what we have this diagram here. Now, as I said, positive downward, meaning that the f body mg will be positive, but anything else will be negative. As you can see in this equation, the drag force is here. Drag force is proportional to the speed to the square, the velocity of the ball to the square, but it's also a bunch of other parameters, that the density of the air, the area of the ball hitting the air, and the coefficient of drag. And so that end up being the drag force. Now you don't see here the buoyancy force because it's so tiny, almost negligible as compared with everything else, so it was eliminated. Now if you substitute that by f net, and that's what we got here, we end up on this differential equation. And so if we follow along, that differential equation that is right here, you can combine parameters here and there, like for example mg divided by m. The m is gone, so you end up with a g, but now you have all this bunch of parameters that in most cases are constant. So you have the 2 here with the m down here in the denominator, but then you end up with the rho, cd, the area, and all these parameters that can be put together in one variable to make life easier. So you end up with rho cd times the area of the front divided by 2m. Now you substitute this bunch of parameters and include the variable beta as to group all these parameters, you end up with this very simple differential equation that says that the change in velocity of the baseball equal to the gravitational acceleration minus beta times the velocity of the ball square. The initial condition for this problem is that time equals 0, the ball speed is equal 0. So you are dropping basically the ball from a given elevation to the floor. Basically, that's what it said. Now, how are we going to solve this equation? I have put some old videos that shows how it was done. I did it using analytical method, or you can use Ron-Yakuta. On this particular case, I'm going to be using Euler. It's very straightforward, and it's going to be shown like here. The Euler method for first order differential equation, and basically you have this differential equation with the parameter beta, but then you have to convert this to this kind of algebraic expression of the differential equation. Basically you do separation of variables, you integrate at both sides, and you end up with this equation that clearly says that the ball speed at a given time is equal to the ball speed at current time times delta t, and we take this g minus beta b squared as the parameter that will change as per our new ball speed. So that's basically it. There's nothing more into this except that we need obviously all the parameters they are right here. They're the density 1.25. I'm using metric 1.25 kilograms per meter cube. Acceleration 9.81, coefficient of drag around 0.5, ball diameter for a baseball is 0.0745 meters. the ball frontal area based on these diameters, about that number that's shown there, meter square. The mass, 0.145 kilograms. Now, if you take all those parameters and put it right here, you will calculate that data is that value there. Now, I also have something here called terminal velocity. Terminal velocity is a very interesting term, and basically it says that in one point in time, this differential equation, this part here, the change on velocity versus time, will go to 0. So the rate of change on velocity will stop. What that means is that g minus beta b squared equals 0. Now you can then, put the equation in terms of the velocity, and that end up being this, and that's called terminal velocity, because the speed, you are no longer increasing your speed you start from 0 and you go along increasing your speed until you stop increasing that speed. All right. There's other bunch of stuff here. I don't care about them, like for example this one here, but this is important. Delta t. What delta t we're going to be using for our system, because that's a parameter that the Euler method is very sensitive to, that delta t. I'm going to start with a 0.1. And why 0.1? That's it's like you can guess this value from the same differential equation. Basically, you can go over here, like for example in that initial case that the velocity is 0, you end up dv dt equal g. Now if you break for delta t and you want what is the precision that you want in this calculation, you can say that delta b might be like 0.1 or something, or 1, at least change from 1 to 1. If you say that delta b is going to be 1, then you end up that 1 divided by g, that's basically 10. 1 divided by 10 is 0.1. That's precisely what you got here, the 0.1. All right, and that's again is something that you need to guess at the beginning to see how well the integration goes by, but eventually you can fine tune to a better value, either make it smaller or larger as required. Now, with that said, we're going to copy all these and we're going to go to Excel, because basically to solve this equation, we need to prepare a table, and I'm going to show you how that's done. So from now on, let's go to Excel, and here we are. We are in Excel ready to do this. The first thing that we're going to do is the same that we have here for what we need. Parameters, let's see how this looks like. Let's put parameters. And then let's double click here, and after parameters we want to put value and units. Units is a reminder that you're in the metric system, and this is density. I call it rho. You can call it anything you want, or density, you can write it there, 1.25. And then the gravitational acceleration and coefficient of drag, 0.5. That's a dimensionless, it's a dimensionless parameter. And ball diameter, in this case 0.745. Frontal area should be like a disk. Let's see, equal pi time this to square divided by 4. 0.436, 0.4369. I can put another one here. Let's see, there we go. That's where this number comes from. And now what about the ball mass? It says here that's 0.145. And what else? Now, the calculation of beta is simple as taking all this that is there, so that's rho times coefficient of drag times the area divided by 2 and divided by the mass, which is the number here. I cannot, so that's gonna be a B7, and that's where you end up. 9395, 9395. Yep, good. Now with that, I can calculate the terminal velocity. Terminal velocity. Let's pop this bigger, looks better. Terminal velocity in this case is gonna be, you're gonna break for the velocity here, so that means that this term go back here and you end up G, basically, put a parenthesis here, a G divided by beta. It's right here, that's BA. Close that parenthesis, the square root of that, 0.5, and that's meters second, and that's the terminal velocity for this system. Now let's get the units here. Kilogram meter cube, density, acceleration, that's meters second square, coefficient of drag, no unit, ball meter, that's meter, frontal area, that's meter square, ball mass, that's kilograms, and beta might have some units. I don't care at this point. In fact, let's see if I can, no, I didn't care to put them here, but beta definitely will have unit, and I believe by checking these eventually you need to ensure that yes, beta will cancel out somehow the unit of the ball speed or the velocity, to end up having at the end all these will have unit the same as meter per second square, because you are adding here G, which is acceleration, so you need, this term need to be acceleration as well. So apples to apples. So eventually the whole thing have to have the same unit as G. Now I didn't care about getting beta units at this point, but you know, be careful with that. So I guess that we are ready now to do this. Now delta T for this problem, I said it's gonna be 0.1 at least, and that's seconds. And now we are ready to get this better, looking much better now. Whoops. Let's see if I get this right. Looks much better now. This is the story. We're gonna get T and the velocity, and here we go. This is an initial condition that at time 0 the velocity of the baseball is 0. So what we're gonna do now is we're gonna run on the time as per the delta T. So this is gonna be this one, the old one, plus whatever delta T I'm using, and that need to be put a dollar sign because that's gonna be constant. So when you run this, it will advance, you know, 0.1, 0.2, and keep advancing until whatever time you need to go. Now on the other hand, this part here is you are applying this algebraic equation that you have here. So that's gonna be the O speed times delta T times, careful here, parentheses, now you can put a G minus beta times the velocity here, which are hard to, I don't think that I can pick it from the way it is, but you can put it right here. So that's B 14, but that B14 had to be square, careful there. And now close the parentheses. Before you do anything, there's something, there's some parameters here that will not change as you drag this along. This will change. B10 cannot change. That's delta T. How about B3? Cannot change. That's a gravitational acceleration, so that will not change. How about BA? BA is beta. That's a parameter. Can change either. How about B14? Oh yes, that will change. That's the velocity. So I guess we got everything that we need, and we hit return. And that's the first speed that we're gonna get, or the first velocity at 0.1 of a second. That's how fast the ball will go after 0.1 of a second. Now, the idea is this: if I screwed up what I'm doing here, definitely this value will never show up on my table. So eventually, what I'm going to be doing right now is dragging this and ensure, taking a look that at the end of this run, I see this parameter. It's a way kind of to check that your delta t is small enough to capture what's going on with this differential equation, and that you are right. I mean, that the result eventually, when I start to drag these, you can see that the velocity is increasing. Now I can take both of them. From here, actually, you can go back here. Like, for example, this already has an equation, and this already has an equation as well. You can take both of them together, here, and you can drag them a little bit. As you can see now, basically, now take a look here. This number is changing, but very little on the decimal, and it's about hitting the 32. I can still keep going a little bit more, and now you can see 6036. Now it's changing the last decimal place. So pretty much within 35 seconds, you are in the terminal velocity. And now check that number: 30 at least 4 decimal places. 31, 41, 31, 41. Go back here. 31, 41. See, it's perfect. It's doing a great job even with such a, I would say, large delta t, but it get the job done. And so it's pretty much heading to the 7 right at the last decimal place here. So let's see, let me run it a little bit more, but I don't think that is important. Yeah, right there. 607, and that's about 0.1. And the 0.1, remember, I got this number based on the fact that I punched the initial condition within this equation and resolve for delta t. So that's the story. Thinking that I want to have what I call the precision on the change in the velocity of the ball, about 1 meter per second. So that's what end up. If you want more precision, then you can drop this to a smaller value like 0.05. See, now you are about half of a meter per second right there. But the end result will still be the same, or even better. Well, in this case, you still need to go, because you are still a few seconds away to get to the final here. So that's the bad part, is you drop the delta t. You make it too small, then you gotta run this table longer. But I mean, this is Excel. When you get your equation done in the first row of the calculation, below the initial condition, you are ready to go. So the next thing here we're gonna do is grab all these two things and make a graph out of them. So let's see how I do that. Let's see, let me go back here, because maybe some of you guys highlight this first row and then Control Shift down, and now hit insert, and now what do you want to do? Curve. What type of curve we want? Could be like this, or could be like this. Actually, let's do that one. So that's basically it. This is how that looks like. And actually, let me put it close to anywhere here so that you can see it. Paste. So here we are. And that's how our differential equation was solved. So we can pretty much, notice that at 10 seconds pretty much is at the terminal velocity. It acquires terminal velocity quite fast, starting from 0. What will happen if I start at the faster, at the high, if I launch the ball downward? at time 0, I have a kind of an initial velocity different from 0. Let's say I put I don't know, 100. That's what's gonna happen. You still gonna end up at the same terminal velocity. Now you launch the ball at 100, but it start to kind of slow down faster until you pretty much within 5 or 6 seconds you are right back to where you are. You see, because the steady state value here does not depend obviously on the initial condition. When you get the steady state, meaning that this part is gone to 0 and you resolve for the velocity of the ball, you end up with the same 32.3141 terminal velocity. So you can start faster, like for example 200 meter per second, but you will still end up in the same place, about 32. That's basically it. What we're gonna do, just to ensure that we get this straight and that we don't have any goof up, I'm gonna do this using Simulink. And for Simulink, 2 things I'm gonna do right here, and let's go back to here. So I got Simulink here. Let me open this big so we see what I'm doing. And basically the idea is this. V prime is the differential equation. You need to integrate that differential equation. When you integrate that, it provides the velocity of the ball. Now that velocity, the way that Simulink works is you have to set up everything that is needed for dvdt. It's like dvdt equals, if you remember, basically what I have here on the MATLAB function is the equation 9.81 minus beta times the velocity squared. So in other words, 2 parameters. Either that's the velocity and the beta. And the idea is, if I go back here, those are the one here. The velocity is coming from here, and beta, that is the parameters that you just punch whatever number you come out with. Like for example, if I go back to Excel or put this kind of smaller so I can see it here, basically that's 0.0939. I should add the 47 here, and so to get more precision, that will do. Let's apply that, say okay, and now we have that number. If I run this, I should get obviously the solution for the ball falling from an initial velocity of 0, because that's the idea. Now few things here and there. So we want to get the data from the scope into Excel. To do that, double click here. It pops in another window, so I gotta redo this again because sorry for that. So this is what I'm saying, and let me get a couple things here right, because there's something is out of order, so you see what I'm talking about. This is what I was saying a few minutes ago, that unfortunately it was not recorded. So like for example, when you open the scope, if you have already run something, it will show up. But the important thing is that you go back here. When you go here, and I'm gonna do it again, let's see, this window will pop. So let me see if it pops in the right place back again. There, now it's popping in the right window where I'm recording. So what I was saying is go to login and login. Set the name that you want. I just leave it the way it is here, scope data, but then set to array. That's very straightforward. It will prepare for you an XY type of a table, and just say okay. And now, as you can see, I already run it. So, but let me run it again. I can change anything here, and it will change the curve. But let's run it again so you know what's going on. Let's see, run. And pop here, and there's your data. Now here's the story. The data is on MATLAB, not in Simulink, so you gotta go to your MATLAB, and let's see if I can move my lab right there, and my data is right here in the, and now let's see, scope data, and there is the table. And in the table I have start from 0 and it moved the delta t, but eventually start to get good values, and to the end about 30. That was the timing that I provide, 32.1, 31.42, and I can copy that, data up to there. So we copy, and now we go to Excel, and in Excel what we're gonna do is gonna put that data somewhere here, paste, and now we have t versus the velocity of the ball, but this was calculated by Simulink, and we want to see how good or bad is this data that was previously calculated by Euler. All right, so now we're going to graph that, so we're going to add that here. So we're going to select data, and now we're going to add a new one, and for the X we're going to pick from here down to the bottom. That was Control Shift down, and now for the Y, go back again to the top and step here. Now Control Shift down, and you have both, and let's put a name here. This is from Simulink, so we know what it is, from Simulink, and we say OK, and we graph, and let's see. And you only see, the funny thing is you only see perhaps only one curve. We gotta go back here and let's find out what's going on, because you cannot see the other. Select data, I got both them plotting, good. So let's see, let's go back here and change city chart type, and I have them, both them, and scatter with smooth. One of them gotta go to this, and from Simulink is coming as is orange. You can do a secondary axis, but would that do it? No, that would not do any good, because I would definitely want to go through so it would look good. Well, basically folks, identical. I mean I would have to use a very bad delta t here so that the blue curve will fail to follow the orange. Like for example, I put let's put 1 second, let's see how bad it is. Let's see, with 1 second it's moving, you know, but it's pretty much copying the whole thing, and even with 1 second it's doing a great job. The only problem here is that I'm moving way too far away from what I would like to see. Is getting to a maximum. Let's see, let's fix that to 30. So there we go, and now we can see what's happening, you know, with the data between the blue points, which are Euler, and the orange, which is from Simulink. As you can see, there's some failure right here. If I get this bigger, perhaps 2 seconds, maybe that's very too bad. Yeah, 2 seconds is too bad, not good at all. Although it doesn't miss the steady state value, it's just the dynamic. You are not capturing properly dynamic, so 2 seconds is way above what you should have. So let's go back to 1 second, getting better. Let's drop to 0.5. Even better, let's drop to 0.1. Obviously you don't see the orange anymore. That's perfect, and that's was the value that I start. If I make this smaller, 0.05, you can see the orange now, but it's just perfect the way it is. It's just that I need to expand. Maybe 0.1 is perfect for this, and get the whole thing covered, the whole up to the 30 seconds. But you can see that basically the steady state is obtained very quickly, pretty much within 10 seconds. This is not changing much from the value that we calculate from here, the terminal velocity of 32.31. Well, folks, that's more than enough. Anything else? Nope, we are done. Have a great day and thank you for watching. Bye.